Hello everyone. Our next speaker is Giovanni Rosso from Concordia, and he will speak about Drinfeld modular forms, old, new, unknown.
Yeah, well, thanks Antonio for the invitation and well, for putting me on the schedule. And so, first of all, everything I'm going to talk about today is going to be joint work with Marco Bernicol. I should have written it in the abstract first. And the topic is, as is talk about Drinfeld modular form. Well, he was talking mainly about Drinfeld modules, and I'm talking instead about Drinfeld modular form. So what is our setting? We start with A is the ring of integers of a function field. So for simplicity, you can think of it as fp of t. And this is inside our field K, which for simplicity, I'm just going to write fp of t. And then we consider an ideal Gothic P inside A that is going to be principal, generated by an element pi. And what we want to study today is congruencies modulo pi of Drinfeld modular form. So what are Drinfeld modular form? First of all, we need to start with the Drinfeld modular curve. The Drinfeld modular curve, you should think of it as the classical modular curve. It's just that parameterizes instead of elliptic curve Drinfeld modules. And how should you think of a Drinfeld modules? Well, a Drinfeld module is kind of a GA analog of an elliptic curve. The idea is that you have GA with an extraction, which is given by multiplication by element of A. And this is our Drinfeld modules. And I'm going to consider my curve X is going to parameterize Drinfeld modules as it is a curve only of rank 2. Somehow this should be taught as the height of my, if you think of formal group, this is an analog of height of your formal group. And so my X is going to be a curve. And over X, I can build some line bundle omega k, which are line bundle of Drinfeld modular form. Exactly as in the classical case, you can see modular form as functional elliptic curve and invariant differential, which are homogeneous over weight k for a certain action. Here we construct a line bundle which trivializes the differential on GA, and then we consider a section that are homogeneous of weight k. And so what do we want to do? Well, we want to study, as I said, congruencies modulo P I of Drinfeld modular form of different weight. Drinfeld modular form of weight K, for example, in K prime. So the first things we should try to do is to find the space. Oh, well, the Drinfeld modular form are just NK. It's just not going to be nothing else than the global section over X of my sheaf omega K. So how can I compare Drinfeld modular form of different weight? Well, the trick is the same as in Ida theory. We consider now our Drinfeld curve X, which I'm going to draw as something like this. And I'm going to consider the ordinary locus. Here I'm looking X, well, now X is rather than as a form over the formal spectrum of ZP, of A. I'm going to consider my curve over the formal spectrum of A. So it looks kind of, I have a special fiber that I'm going to draw in red. And in the special fiber, I have some super singular points. And so what I consider is the ordinary locus, XORD, which is nothing else than the counter image of everything which is not super singular. And why is this interesting? because over XORed, well, every Drinfeld module of rank 2 has the following p torsion. What is the p torsion of a Drinfeld module E that is ordinary? Well, it is the extension of an null path, and the connected part is nothing else than the Carliph module, the p torsion of the Carliph module, which is some sort, you should think of this, the Carliph IS module is some sort of analog of GM. I say an analog of GM because GM, you know that the torsion of GM generates the abelian extension of Q. The torsion of the Carliph module is a Drinfeld module of rank 1. It generates the pi torsion, it generates the abelian extension, for example, of P of T. Okay, and so what I can do, I can define over my XORed a new space that I call IG, which is nothing else than the space of isomorphism between the connected part of the pi infinity torsion of my Drinfeld module and the p infinity torsion of my Carliph module. And so this is now a torsor for A localized P star, because this A P star, I take my ring of integer AF, P of T, I localize complete the ideal corresponding to pi, and then I take the units. These are the automorphisms of the space here. And so what I get, this is just be an A torsor. And the nice thing is that I can consider the direct sum of mk over all k greater or equal than 0. This embeds inside the function of the Gusa tower, which I'm just going to call m pi-adic. And it is dense image. So I've created a space of pi-adic Drinfeld modular form where classical modular form embeds and where they are dense. Okay, and so now the trick to do the theory is, well, let me state the theorem first, which is with Mark-Huber. There is, the first property is that there is an ordinary projector let me call it E, which is kind of u pi p to the n factorial, well, the limit over n. So I take the equi operator at pi, and I consider I iterate it many times. This iteration makes sense on my space of p-adic modular form. And what is this the property of this operator? If I take E m pi-adic, is a finite rank, finite type module over the Iwasawa algebra of A pi star. Indeed, because over this space m pi-adic, I have an action of A pi star, and so I have my nice torsor. And this action commutes with the equi operator, so I have an action there. And the good thing is that this module is of finite type over this algebra. And the other good news is that if I take this ordinary module and the tensor, let me call this lambda, over lambda in weight k with A pi, I get back the weight k form, which are pi ordinary. Here, the morphism k from lambda into A pi is, if I take a gamma in the group A pi star, is mapped to nothing else than gamma to the k. And so this is we could call this Ida theory for Drinfeld modular form. And because somehow we see that if from a huge space of pi-adic modular form, we can cut out using a nice projector a relatively smaller space that interpolates all the space of classical pi-ordinary Drinfeld modular form. And now just a very important remark is that what is this lambda? Lambda is isomorphic kind of to a pi, a product, a finite number of components of T1, T2, and so on. Contrary to the classical case, where ZP star is known to be practically generated by 1 plus P, this group, A pi star, is as a ZP, as a topological group, is isomorphic up to a torsion part to infinite many copy of ZP. So my Wasawa algebra lambda now is going to be isomorphic to formal series in infinite many variables. So it's kind of a unit ball in infinite many dimensions. The good news is that these points are still dense. The integer weights are still dense. And so this module is completely determined by the classical specialization, but still we have plenty of new strange pi-adic forms. And we don't know much about it. For example, we can construct a Galois representation. Somehow we construct the representation interpolating classical representation and then specializing a classical weight, but we cannot say much. We don't know much about it. Already it's not known much for the Galois representation associated with Drinfeld modular form. They are simply character. If I have F, I can associate it rho F, which is from G of K into, well, J1, for example. They are just character, but still we don't know much. And for example, it would be nice to know more about the Galois representation associated to this. Okay, and so now I've given you something which was new and something which was old and something that was unknown about ordinary Drinfeld modular form. So the next step is what can we say when our form is not ordinary? Now take F classical Drinfeld modular form. We suppose that UP of F, weight K if you want, is equal to A times F. A is non-zero. Classically, we know that if this was an elliptic modular form, thanks to Coleman theory, we could find a family of finite slope, an analytic family of finite slope over convergent modular form. So can we interpolate this in family? And so how would we go? We go back to our nice picture of our Drinfeld modular curves. I've drawn for you before the supersingular locus, some disk of Drinfeld module with supersingular reduction mod 3. And classically what we do, we have our ordinary locus, which is nice and green. We try to consider form that extend a bit inside here. So we would like form that I can extend inside a bit in a small annuli in the ordinary lock, in the super singular disk. So we consider overconvergent Drinfeld modular form. These are nothing else than F, p-adic modular form, which extend to some super singular annuli. And maybe we can interpolate over convergent Drinfeld modular form. So the idea is that you take kappa, an analytic character of A pi star into, I don't know, K bar star, completed, analytic character. And let me just denote by XV this new overconvergent space. And what we would like to do is to construct a shift omega kappa over my XV. And the big problem here is that kappa analytic implies that kappa is an element of ZP. As before, we had the character that was sending gamma into gamma to the K. The only character which are analytic of A pi star are gamma goes gamma to the S with S in ZP. And so, well, we still get something. We can, if we consider S the universal weight, which is somehow the generic element of ZP, we can still construct omega S over XV times the locally constant group scheme ZP, such that if we take its global section, what can we do when we take the global section of this? It is UP acts on this space completely continuously, well compact. And we can define slope decomposition. And so the second theorem is that we have always joint with Marcoubert families of finite slope form. But now what is the, well, with coefficient in what? Continuous function from ZP into A pi. So, well, if one study this as a locally group is a group scheme, locally constant group scheme, you see that the function there are nothing else than the continuous function from ZP to AP. And so somehow we are a bit weaker than in the case of Coleman family. And so the natural question is, can we upgrade our families to something better? Somehow, let me draw the last picture of the talk. I have my nice infinity dimensional ball. Which is somehow the lambda, is the spectrum of lambda. Inside there, I have ZP, which is a bunch of points goes around like a spiral because they are Zariski dense. And somehow, what I have when I have Ida theory, I have a nice function on this infinite dimensional ball. But when I do finite slope, I only have function on this sort of, well, it's not discrete, it's Zariski dense, but it's just kind of a small spiral. And so the question is, can R, the coefficient, more than continuous? For example, can they be upgraded to some sort of function where somehow we have our C of ZP AP, which is, I can embed lambda inside there. And is there a space inside that is geometrically nicer maybe than just this ZP? And well, this is another open problem and no things that we don't know. And in the last minute, just one other things. Another fact, we can consider modular curve X of level pi to the n. And we can consider the projective limit as a topological space. Well, this is isomorphic to some sort of X infinity, which is a perfect Hall space. And well, this is another theorem with Mark-Huber. And what we show is that we can recover over the perfection of X using perfectoid methods our sheaf omega S. The omega S that was defined a priori using geometry can be, well, at least its perfection can be defined using perfectoid method. And so, well, this is another open problem. Can we do this? Can we do something more with perfectoid that we couldn't do there? Oops, can be defined using perfectoid method. And so the natural question is, can we do something more? Can we, for example, recover directly from this x infinity, the sheaf omega S without the perfection? And this is another unknown things over which I want to finish my thoughts. Thanks.